Good morning. This is the seventh lecture of the series, X-ray crystallography and solid state chemistry. We talked about it a little bit in the last lecture, but then I told that I'll be repeating these slides so that we get continuation of it. Well, it is a space group presentation, and we are talking about triclinic space group P bar 1, and the number is number 2. As I said, that we have 230 space group. So numbering started from triclinic space group, and this is second space group of the 230 space groups. And we have also discussed a little bit how we show in the two-dimensional thing, and there we do dictate by some rules, international rules and convention to describe the space group. So the P bar 1, that is number 2 space group, in summary, we talked about that there are equivalent position. Mind it, we always talk about equivalent position. That means when we determine three-dimensional structure, we have to place our atoms in the I would say symmetrical arrangement. And in every space group, we do have equivalent position, and also general position is equivalent position, also spatial position. So we were discussing this space group, showing you in the right of the figure that center of symmetry or space elements, and in the left the equivalent positions of the of that particular space group. Here we show that there are center of inversion in this place. Let me take the screen pointer. And this is the equivalent position, space element, that there is center of symmetry, which have been shown in this circle, open circle. Well, then we see, according to the symmetry elements, we have only 2 equivalent positions. And what do you mean by 2 equivalent positions? We always talk about unit cell and how many position we do have in a unit cell due to the symmetric operation. So in this case, it is a center of symmetry. It has a center of symmetry, and for in the unit cell we will have 2 positions. That 2 positions are called equivalent positions, and equivalent positions are being expressed in x, y, z, a value of x, y, z, and the value, as I said in the last lecture, the value from 0 to 1. You can take any value from 0 to 1, fractional or non-fractional value, 0 to 1. So x, y, z, and it is also told that this origin is taken very close to the this left corner of the parallelogram by which we are presenting the space group. That we take the origin over here, and then the symmetry operations tells us how many equivalent positions we will get. In this case, we get 2 equivalent positions, x, y, z, and bar x, bar y, bar z. I have to tell you here that it's always, for me, that difficult to show you in bar x, bar y, bar z. Therefore, in many cases, we will see that we are talking about 1 minus x. 1 minus x means bar x, 1 minus y means bar y, 1 minus z means bar z. So we have to remember this. Now, one center of symmetry to generate the equivalent position in space group P bar 1, many other center of symmetry are created automatically. many other center of symmetry created. Example, the center of symmetry at U, here at U, arises because pairs of position such as we see 1 and 3, 2, 2, 3 prime, 2, 3 prime. This is just a notation we have taken. Because of this U at U, there is a center of symmetry, and therefore this point arises automatically this point. Okay, so we may see this in the diagram, as I said. Next we go, the position 1 and position 2 are general position. These are general position. And as I said, the value x, y, z can be between 0 to 1. In certain circumstances, x, y, z and 1 minus x plus 1 minus x half 1 minus z. This half is the value of y. Coincides, for example, when x is equal to y is equal to z is equal to half. You see, if we take this point is half, this point is half, this point is half. So in this case, they are only in the position half 1, half, 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 half. This coincides and the position becomes half, half, half. And that is called spatial position. Another thing, spatial, a general position, if it lies on a center of, on a space element or a point element, lies on a space element or point element, then it becomes spatial position. In this case, the spatial position is half, 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 so forth. I said this already. Yes, spatial position arises when the general position lies on a symmetry element. Is it not? So if we see the spatial position of space group P bar 1, we have these are the spatial position 0, 0, half, 0, 0, 0, half, 0, 0, 0, half, 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 0, and half, 0, half, 0, half, half, and half, half, half. And these positions are where it is in the corner, edges, face, and body center. You see, in the corner we have a we have this spatial position is lies on the symmetry, just on the symmetry element, and then we call the edges. It's on here, and then we call also faces. That's here, and then these are the spatial position of this space group P bar 1. Okay, well, this coordinate of general and spatial position of each space group, in each space group, remind this, it's each space group that are given in the internal table of X-ray crystallography together with additional information. In the next slide, we show that position, how it is shown in international table, only taking this example. Okay, this is how it is shown in the international table. Well, this is the table where the general position and equivalential positions are shown in space group P bar 1, which is number 2 space group. Well, this first column here, the first column is the multiplicity column. That is number of equivalent position. How many number of equivalent position is that? And second column is Wyckoff notation. And this Wyckoff notation is inverse alphabetical sequence. That means we start the last one from by A, and then going to the column, we start B, C, D, E, F, G, H. So that is what is Wyckoff notation. And this third column is point symmetry. What are the point symmetry belong to this number of equivalent position. And the last column is the column for coordinates of equivalent positions. So for this space group, specifically, how it is, the number of position 2 is the general position, and it has a Wyckoff notation is I, and then point symmetry, it has no point symmetry, you see. One is not a point symmetry. One is a identical, if we rotate a object 360 degree, it becomes identical. So therefore, point symmetry are in P bar 1 for equivalent position. 2, there are no point symmetry. But coordinate system, already we have said the 2 coordinate system, x, y, z, bar x, bar y, bar z. Next, we have spatial position. So it started from here, you see, and in this space group, only point symmetry is center of symmetry. Therefore, we are seeing here bar 1, bar 1, bar 1 only. There is no other point symmetry, and it starts from 0. This is the highest symmetry one, and then the lower the symmetry, we go up in the table like this. So this equivalent position for a spatial symmetry for this one, and then this, then this, then this, what we have already discussed. So this is how the table in International X-ray crystallography table showed the general position and equivalent position for a particular space group. I say this is the one which is for space group P bar 1. Okay, that's what we have shown now. Now we are going to another space group. I said we will be discussing around 2 or 3 space group, and then with this knowledge and with this convention, you have to practice yourself by going through international table for this space group representation, how we do it. We have already discussed the laws and the points we have to remember, how one has to do this diagram and explain this. The second space group is a C2 space group. We said, if you remember, that a space group is represented by 2 to 4 figure, and the first one is the lattice type, and capital lattice type. That means the lattice is side-centered lattice. In this case, sides are C-centered lattice. So we have a C-centered lattice, and this is the symmetry element. So we have a 2-fold rotational symmetry in this space group. So it is, the number is number 5. Whenever you just open international table, you will see that this number 5 is represented there in the international table, and giving all this detail, what we have to remember, which sign is there, which sign is for what, etc., etc. Well, for this space group, by convention, you see, we have a unique axis. Unique axis means that this is a characteristic axis for this particular system, or this particular crystalline system. And it is a monoclinic system, and it has got a unique axis, 2-fold axis. This unique axis is labeled as B. So, okay. Now you might ask, what is a unique axis? Every crystal system has got a unique axis. Unique axis means if we have, I repeat it again, if we have a axis by which, by convention, we can take all this space group properly, discussing, specifying the axis, and then in the monoclinic axis, the convention is that we take 2-fold axis as the unique axis, and that is labeled as B. That means it's parallel to B. Okay, but this is different from other practice, unique axis practice. For example, tetragonal, trigonal, or hexagonal cells. If we have tetragonal cells, trigonal cells, or hexagonal cells, there we do not take unique axis as B. We do take unique axis as C. This is the difference. It is by convention, we have to take B is the unique axis for this monoclinic unit cell. And in case of tetragonal crystal system, trigonal crystal system, hexagonal crystal system, we have to take C as the unique axis. Okay, with this convention for C2 space group, what we have with B as a unique axis, the unit cell projects. How we project this unit cell? We project it in XY plane as a rectangle. Why XY plane? Because in that case, gamma is 90 degree. So since we said in our definition that monoclinic has a axis, interaction angle beta, which is greater than 90 degree or not equal to 90 degree. And this z-axis is not perpendicular. Therefore, z-axis, if it is not 90 degree, it is not perpendicular to the plane of paper, but it is an inclined vertical one in the plane of paper. Okay, we have now discussed about the convention. We have now discussed about this space group, how we use. Well, you see, we said once we have a space group notation, we immediately find out the point group. What? The point group, when we have a space group, we do not take the lattice type. If we do not take the lattice type, only take the rotational axis, then it becomes the point group. That is, in this space group, the point group is 2. And the point group 2 means that it's a monoclinic system. So from the space group, we can immediately find out what crystal system it is. So we do not have to have any confusion here. Okay. So I said this is the lattice point at the origin. Let's say that we are talking about a lattice point in this space group, and which we just fix at coordinate 0, 0, 0. It is just a convention. It is just a convention. So it has also an equivalent lattice point where, and so an equivalent lattice point where is half, 0. That means x value is half, y value is half, z value is 0. Okay. For any position x, y, z in this space group, there will be therefore an equivalent position x plus half, y plus half, and z. Any position. Well, I hope this is understood what we are talking. Now we are talking about symmetry element. What symmetry element do you have? We do have a symmetry element, twofold symmetry element, and it is parallel to y, parallel to b. B means y, parallel to b. This is a twofold symmetry, notation of twofold symmetry. This is a notation of twofold symmetry, an arrow which shows the a pointer with arrow which shows that it is a twofold symmetry. What other symmetry we have when we do rotate this twofold symmetry, we will see that there are other automatically created symmetry elements. In this case, we will see that there is a screw axis, twofold screw axis, and it is represented as half arrow. You see, we will have a twofold screw axis in this 1/4 position, also in the 3/4 position, parallel to y. That's what it is, what we have discussed here. Okay. As I said, the other symmetry elements are generated automatically by combination of twofold rotation axis and a C-center. These other symmetry elements are a twofold screw axis. So that what is how we explain this one. This is the symmetry elements shown in the space group, and these are the equivalent positions shown in the space group. We have 4 equivalent positions if we do so. That one is x, y, z, as generally was what we said, and then we showed this is The next one is minus x, minus y, minus z, or we call it bar x, bar y, bar x, y, bar z. I said that in the beginning that bar x, bar y, bar z means minus x, minus z. But I would not say means. I would say the notation is shown as minus x, which is bar x, y, minus z, which is bar z. So this is the two equivalent position. One is this, another is this. And then another two equivalent position, x plus half, y plus half, z, and then minus half minus x, half plus y, and minus. These are the four equivalent position. And then we have also special position, where for point symmetry 2, as we said, if the if the symmetry lies in a operation, in a line of operation, that here it lies in the operation line, here also it lies in the operation line, then it becomes special position. So for point symmetry element, we have 2b position, 0, half z, and 2a position, 0, 0, z. If you remember, we showed the equivalent position in space group, in a table in space group p bar 1. So these are the way we discuss the space group in two parallelogram figure. Right one is always the showing the space symmetry elements or symmetry elements, and the left one equivalent position. So how it gave the equivalent position. We discussed it here, how the equivalent positions are created in this space group. And now I already mentioned a little bit about it. Another space symmetry elements, two-fold screw axis, have been created automatically in the space group C2. This two-fold screw axis involves a rotation of 180 degree and a translation of half position in the unit cell in the direction of the screw axis. That's what is it. We said there are another two-fold screw axis automatically created, that is parallel to B cut. Parallel to B cut. This is parallel to B cut. So at the x 1 foot and 3 foot, and they are in the plane of the unit cell, and the projection at z is equal to 0. This, as I said, this is a half arrow screw arrows, which is shown as the screw axis. So that is also I have discussed a little bit, and if you go through this, you can easily get the explanation of these two figures. Okay. Next, we are yet talking about it, and in summary, we say that the C2 space covers 4 equivalent positions, which we showed here, 4 equivalent positions, and then due to two-fold rotation, and then automatically displayed some other equivalent position, which we showed here in point symmetry 2, 2b, 0 half z, and 2a 0 0 z. That's what we discussed, and we said in figure created translation to adjust the unit cell. The other two-fold rotation and two-fold screw axis are generated automatically and do not generate any extra equivalent position. I have a little bit cold, and that's why a bit problematic in clearly talking or something like that. Let me take a little bit warm water. Okay. That's what I said already, that there are 4 equivalent positions, and these 4 equivalent positions can be described in 2 sets, x, y, z, bar x, y, bar z, x half plus half, y plus half z, and half minus x, half plus y, bar z. The second set is related to the first set by lattice centering. That is by adding half, half, 0 to the coordinates. It is common practice in international table X-ray crystallography to list those positions that belong to the first set. We have said two sets. The first set will be discussed in international table. General position in space group C2 are fourfold, but if they lie on a twofold rotation axis, I'm sorry for the little bit cough and cold. I repeat this, the general position in space group C2 is fourfold, but if they lie on a twofold rotation axis, their number reduced to 2. And then spatial position, 2 become the spatial position. Thus, X is equal to Z and Z is equal to 0. These two positions have coordinates 0, Y 0, and half, Y plus half 0. A second set of the spatial position, if X is equal to 0, Z is equal to 0, we may read it like this in figure C by 2, X is as X of D. Okay. We completed the description of space group C2, is it not? We will take another space group and then complete the space group description. The next space group will be P2221. Thank you for this class. We'll talk the next space group, that is the orthorhombic space group, in the next lecture. Thank you all.